Okay, kids, today we're going to talk about vectors. What is that all about? What is a vector? Cool. So, in Latin, vector is one who carries or conveys, carrier, takes something from. It's a thing that goes from here to there, right? In math, it gets quite annoying to describe it. It's an object, it's an element in the vector space of a particular, uh, you know, in a particular vector space. In our case, we are only caring about the real numbers. We're not doing complex. We're not doing the combination of real and complex. We are in the real number space. Simply speaking, in more layman terms, a vector is really a change of position, right, in n-dimensional space. So a one-dimensional vector is, you went from 1 to 4, your vector is 3. That's the change. That from going from 1 to 4, you need 3 change. You can do this for any arbitrary dimensional space. So a vector has a direction, right? In the case of the one dimension, you have positive or negative, right? And then you've also got a magnitude, and that's the size. So a direction is a heading, it's the rotation, whatever you want to call it, and the magnitude is the distance, the length, the force, all of those things. And this is actually a very, very useful idea to be able to move things around the screen or move things in graphics programs. And so the magnitude's pretty straightforward, right? Like to capture the magnitude is just using the Pythagorean theorem. You just take the square root of the square of the x and y displacements because it creates a triangle, and your magnitude length is going to be based on the Pythagorean theorem. Here's a little video. It's in the lecture slides if you'd like to check it out. So vectors are quite useful to encapsulate really motion and information that you want to have in your application. Like for example, our x coordinate could be replaced with a vector. Our speed, acceleration, the friction, the opposing force, the wind, the opposing drag, all these things can be used and represented as vectors. If you kind of think about the corollary of like free body diagrams in physics, if you did that in high school, that's the sort of, you can draw these things and then the output is just the sum of all of them, right? So a velocity vector is really kind of this relative vector. It doesn't have a position on its own. It is applied to a location. So you have your point of origin, and then you apply a vector, which you just add that vector to that point, and then you get a new location. And all it is a change in y and a change in x, or in whatever number of dimensions that you may be in. A position vector is just really a displacement from the origin, if you want to think about it that way. So this is actually something that is really important, I think, in graphics in general, which is you sort of need to know what your reference frame is in your base, because everything is a lot easier to do at 0, right? If we treat our object as in position 0, we can rotate about that position or whatever, but then we have to move it to where it actually is when we render it, right? And so a position actually is a vector in the context of a graphics application, because all of our objects are going to be created around their own respective origins. And then you'll see this happen in nested architectures, where you have like these objects which are part of a bigger object, which are part of a bigger object, which is part of your world, which is the object that contains all. So a position can be represented as a vector, but you'll notice there is usually a differentiation between a point and a vector in a lot of graphics applications, because a point isn't intended to be used as a change in location, and a vector is meant to be a movement, a relative vector. Now you've got another vector that you see often is a heading, right? Like, where am I facing? So here's a sphere, right? I can rotate the sphere as much as I want. In theory, it should look the same. So a sphere's rotation is sort of arbitrary if you really think about it. But say, how do I know then which direction it's facing if it doesn't have an orientation, right? And so you can use a heading vector as effectively a kind of velocity vector of, okay, well, my ball is here, and it's going this direction. So normalization of vectors allows you to, so this is a lot of the stuff you should have probably already seen with linear algebra prior. And so you probably should understand what normalizing a vector means. Ultimately, a normalized vector has a magnitude of 1, meaning that Pythagorean theorem we saw, right, the x, y, and whatever other dimensions squared, respectively, the square root of that should be 1. To get this actually quite easy, all you have to do is you divide each of the components by the magnitude, right? And then you square, then that's your normal. It's quite easy to do. So why is it important to normalize vectors? Well, it's a lot easier to do a lot of the math that we're going to do with 1, right? Because it just gives you back the same value, than to have like these numbers that we have to kind of keep track of and then sort of retroactively apply. You know, it's kind of like applying these arbitrary magnitudes. It's easier just to deal with ones, in particular for rotation orientation stuff, and so on. So even velocity often you'll find is normalized, and then you apply a magnitude to the velocity. So you have the heading, and then you have your velocity magnitude, and that's more often than not the way you do it versus having velocity as this sort of like thing that scales with like physically or mathematically the way that you would expect to do it on paper. So again, to do the actual calculation of normalizing the vector, you just have to determine its magnitude, and then you divide each component of that vector by that magnitude. And that's generally that's all you really have to do. So, say I wanted to shoot a monster with a paintball, although in this picture it looks like a rocket. The original slides were very like Despicable Me oriented, and I have reduced the amount of Despicable Me, but I like this one, so I kept it in. So say I wanted to hit a monster with a paintball, I would basically figure out in which direction it is, so I would take that position and my position, and I would subtract their position from my position, giving me the respective change of my position to theirs that I would need. So that gives me a vector, and then I would normalize that vector. That gives me a direction, and then I would multiply the paintball, the velocity of the paintball, by that vector, right? That velocity being, in this case, just the magnitude of the force that I'm shooting with. And that way, the ball will be moving in the correct direction at the right speed, as well. I'm not entirely sure what this is. So, addition of vectors is pretty straightforward. You can kind of imagine it like basically taking imagine like toothpicks, and you have one toothpick, and then you take the other toothpick and you kind of put it on the edge, and you just repeat as much as you want. You can prove mathematically, if you'd like, that it doesn't matter what the order is. So vectors are associative, they're commutative. They also, they abide by the identity principle. This is how you prove that a vector space is a vector space, is you have to prove that those things are true. And so vectors also have that behavior of a vector space, which we'll talk a little bit about later, but not to any sufficient degree to really be interesting. And yeah, so what vector would you then do? Like, what does that look like? Well, it just is the combination of the elements. So to get the ultimate x and the x value and the y value respectively of a combined vector, you just connect and add together those components of each separately. So for c, the cx, the x of c is going to be equal to the x of a and the x of b combined, and the y of c in this case is going to be the y of a and the y of b combined. And yeah, this is just an example. As you can see here, c is going to be equal to, in this case we have a 4 and -2, and b is 5 and 8. So you add 4 and 5, you get 9. You add -2 and 8, you get 6. And c is ultimately a 9, 6 vector. Subtraction, it's basically like addition, except you flip the signs of the two. So it's not too different than addition. As you can kind of see here, you would have AB, but instead of adding 4, you would subtract 4. If you, instead of adding 2, you subtract 2. -2, which is adding 2, right? And kind of like the, let's call it the intuition for subtracting a vector is, there's a couple. One is you're actually adding a negative vector. What's a negative vector? A vector is pointing this way, the negative vector is pointing the opposite way. So that's one intuition, is I want the opposite of that vector. Another idea is I can kind of figure out the delta between where I went and where I wanted to go, and so I need to subtract these points from each other to get the vector, the respective vector of what is the difference. Like we were talking about, how do I determine a velocity in the first place, is I would take a point at time time 1 and another point at time 0, and I would subtract the two, and then I would get the delta. And so you can do the same thing with pure vectors as well. Like for example, you have the wind vector and you have your velocity vector, and you can subtract the wind from your velocity, and then you get the effective direction of the plane. Although in this particular picture they're showing a addition actually, but that's kind of irrelevant. So how do you multiply a vector? And I want to really make it clear that we're not multiplying two vectors. We're multiplying one vector by a scalar number, and a scalar number being part of that real number set. So it's like 5 times a vector, or 3 times a vector, or -3 times a vector. And so in this case, you're just taking that value, that scalar value, and you're applying it to the components of the vector uniformly. And so it's almost like, in the case of scaling by 2, like making it twice as long, that's like adding 2 of the vector. You can kind of imagine you're taking one, then you're attaching another one, so it's twice as long in that same direction. But you can do that for an arbitrary scalar as well as negative. If you're going in the negative direction, it's almost like going like this and then going like that, and you're down here now. So yeah, there's a lot of it's very similar to multiplying a normal number at that point. And so if you remember this guy shooting a paintball, we would have to send that paintball at 5 times the normalized vector if it was only at a speed of 1. And so to get there, we could do it. We could just multiply it by 5. So this is something that you can do, programmatically, or you can do it incrementally. If you were to do it programmatically, you would take velocity times 1, velocity times 2, velocity. So don't do that, but that's just sort of the intuition for scalar multiplication, just making a vector bigger or smaller. Vector division, scalar division, it's just like multiplication, it's just the opposite. You're dividing instead of multiplying, or really specifically, you're multiplying it by the reciprocal, or 1 over the scalar. So in short, vectors are super useful for not just 2 unit value units, but 3 and 4 as well, right? Things like location, velocity, acceleration, and obviously very, very accurate containers and descriptors of forces like gravity, wind, attraction, repulsion as well. So, um, to talk about how to program with vectors, a lot of languages have vector 2, vector 3 classes like Unity and C Sharp if you've taken 202, which is the other class I'm teaching this semester. Um, the standard library has a vector library, but the vector library in standard is a vector as in a computer science vector, which is a list that has a static memory. So keep in mind that you don't want to get those two confused. But generally speaking, it's really easy to have a vector class. You can build this out. It doesn't take much. It's an x, y, and z value. And you can have a lot of functions though, like the dot product, the cross product, rotation, converting it into a quaternion rotation. It's a mess. So you can build them relatively quickly, but they're so varied and used that often you want to use something like GLM, or IGM is another good toolkit, or just build it yourself is fine as well. You're just going to have to spend a bit more time in getting the vectors to do what you want when you come across a functionality or capability that your respective linear algebra library does not have, which is what I did. So it's possible. Cool. That's it for vectors, and next we're going to move on to vector spaces. And so I'm not actually going to set a new lecture. I'm just going to do this together because it makes no sense not to create a whole new lecture on here. So let's moving on to vector spaces. So with regards to vectors, and like we were already talking a little bit about vectors and how they work, but in terms of a coordinate system, this is a point in space, and the reason it'll be clear why we're talking about coordinate systems in a minute. On its own, it doesn't really represent anything. It doesn't have dimension. It's just a point. A point has no size. It has no orientation. It is literally a point in space, a theoretical, abstract, mathematical point in space. Yes, it's very stressed out. But when we put it into a reference frame, now it starts to have a bit more context, right? So now it has a x, y, and z value, and it's important. It's clearly a very happy point. So why is this important? If we have 2 points in space, and one of them moved, how do we know how it moved? Like, if they're not rooted in a coordinate system of some kind, we don't have any way to determine that this point is this far and this point is this far. They might as well be exactly in the same place, right? There's no way to really tell the difference. But if you put in a coordinate system, now we know that respective change has an actual associate, like a real value system, like it moved this many units, and we can understand how that works. And so in a coordinate system, we have an infinite number of points that can be represented, and we also have an infinite number of displacements, and we also have an infinite number of orientations and all of that stuff. But as long as we anchor them to the origin, we'll always be able to figure out their new location in space as long as we know how they moved to start, right? So vector, for example, allows us to take a position at 0 and move it to another position in our coordinate frame, which is close, but it's fine. So if I take 2 points and I apply the same translation to 2 points in the same space, there's no way that this could happen. They will behave in the same way, no matter what. If you translate it, if you rotate it, if you scale it, but you said what we were talking about, and you said that they're going to move in the same way, right? Like with the translation case, although this is not exactly, this is a lovely, lovely idea here that they're not quite moving in the same direction, but the idea would be they would move together, like in this translation case, but in the rotation they don't move exactly the same, or if you scale them, they obviously don't move in the same way. So obviously we have to know that rotation and scaling, while being linear transformations, do not produce linear movement in the points, and that's okay. They will transform the same. Great. So let's go back to the 2 points for a sec. Let's increase their position in X. So let's translate them. Okay, that's not quite right. So they need to have the same coordinate system, and this is probably pretty important in that you can very much have points and information in two different systems that are related in some way. And if they are in the same coordinate system, they're going to move the same way. So if they're in different coordinate systems, even though we're applying the same transformation, and that is an x displacement, technically they've displaced an x, but their coordinate system was different. So if you're in the same coordinate system, you can predict that behavior directly. So hopefully this is helpful. This really means to say that vectors, when you deal with them, need to be in the same space. And the mathematical definition of a vector space is such that it contains all combinations of real values or complex values or both. And in this case, you can apply transformations to vector spaces. So this vector space being a rotation of this vector space, technically they are the same set, provably so, but they are different vector spaces. So yeah, that's a little quick introduction to vector spaces. And now we can jump into matrices, which is kind of the last piece of the puzzle that we need to know for this class. So a matrix is actually a combination of vectors. So you can have, in this case, you have an identity matrix of three, three-dimensional vectors in a matrix. But often we represent a matrix as just a rectangular array. We have rows and columns. The way row first or column first is up to you. For the most part, we treat the below as XYZ, XYZ, XYZ. But you can also imagine it's like XYZ, XYZ, XYZ. So it depends on how you implement your code, and ultimately you just have to be consistent, because either one can work fine. You can always translate, or transpose, I mean, the matrices if you run into an issue there. The basic operations of a matrix are very similar to the way that we did it with vectors, where the combination, a particular point where ij, meaning I being the location of row and that j being the location of column, the column and then the row, is just going to be the combination of that respective, row and column combined. So in this case, we have this matrix 1, 1, 1, the 2 on the diagonal. So the top left is going to be equal to 1 plus 2. The one next to that is going to be 1 plus 0, because there's 0 there, and so on. So addition very directly follows vector addition. Subtraction, in the exact same way, it very directly follows vector subtraction. Instead of addition, just like we did before, is just adding. Multiplication. The multiplication of vectors is not a trivial thing by comparison to scalar multiplication. or division of a scalar. Scalar multiplication and division, just for completeness, does just translate directly from vector scalar multiplication and deletion and multiplication and division. But you can actually multiply vectors, you can multiply matrices, but they work in different ways. Now, where if you're familiar with a dot product and a vector, a dot product vector is commutative, but a multiplication of a matrix, which uses a very similar concept to dot product, is not commutative. So if you multiply A times B in that order, it's not necessarily guaranteed to be equal to B times A. There's a lot of ways to demonstrate this, and in particular, when you multiply matrices, which is a bit beyond the scope of what we're going to talk about in this lecture, you know, the inside, so you have a 4 by 4 matrix multiplied by a 4 by 4, that's fine because the two internal ones are 4, right? The number of rows, the number of rows matches, no, the number of columns matches the number of rows. That's what is important. So if you have a 4 by 4 matrix times a 3 by 4 matrix, this will not work. But a 4 by 4 matrix times the 4 by 3 matrix will work, for example. So you have to kind of keep these things in mind. But regardless, two matrices, different directions. I'm sure you guys already know this. So to multiply, again, you need to have the same number of columns in the left matrix as you have the number of rows on the right matrix, because what you're doing is you're actually taking the dot product of this row you're taking the dot product of row 1 times column 1 and plus the dot product of row 2 times column 2, and that's going to be equal to your top left position. And then you're going to rinse and repeat that for the row 1 times row 2, row 1 times column 2, plus row 2 times column 2, and so on and so forth. And for the right one, you're going to be taking row 1. Oh, I'm sorry. I'm totally screwing this up, actually. In this case, you're just taking the row 1 times column 1. That's the dot product of those. Then row 1 times column 2. Then row 2 times column 1, row 2 times column 2. And then those are your respective 4 values, if that makes sense. You can see this example here. Sorry about the confusion. You don't add the dot products. You just take the dot product respectively. Why do I care? Well, your coordinate system creates a effective base or a orthonormal set of matrices. A matrix that is a combination of orthonormal vectors. So, for example, we're gonna learn more about transformations in a next class, but a common orthonormal basis set is just the diagonal, the identity. In this case, you've got the x, y, and z normal vectors, right? Or the I, j, and k unit vectors, as they're called. And that's going to represent your base of your coordinate system. Now, if I multiply a point by that base, I'm going to get that point back because that point is going to be in that coordinate space. But what if I rotate my coordinate space? So my point, respective to that coordinate space, stays the same, but then I can rotate that entire system. And so I can take that unit vector base and then rotate it such that it is now a different base of coordinate. It's a completely different coordinate system. It is rotated. And the equivalent kind of the thing that's important to understand why this is valuable is, say I have a mesh, like a mug, right? I've got my mug, and I'm rendering it, and it's got all this data and all these points. But then I want to rotate it. Like, I don't want to have to calculate for every single point what this new rotation looks like. So instead, I have my mug, and it's in my, identity matrix coordinate system. If I rotate that coordinate system, the mug will rotate as well. And you'll see this in this is kind of the basis of all the transformations that we do. In a way, the transformations in of themselves are manipulations on an underlying vector space that represent a different coordinate system. And hopefully that's not too confusing, but as you do it, you'll find it's pretty straightforward to really understand how these things mechanically function. Yeah, cool. So that's kind of the end of our dive into vectors, matrices, and vector spaces. Kind of a high-level review, hopefully, for everyone. This is not meant to be a linear algebra math class, but very, very helpful if you kind of understand this basics of 3D math that's underpinning a lot of what we're doing on the graphic side. So yeah, hope to see you guys soon.